In this next series of lessons, we are looking at separable differential equations. Now, separating a differential equation is just a little hack that we can use to help solve them. But the important point to start with is that we can't separate all differential equations. They're not all separable, as you'd say. So which ones can we separate? Well, they have to be first order, which means they can only have y dash in them, not y double dash or anything higher than that. And they absolutely have to have this form where the first derivative is equal to some function of x multiplied by some function of y. Not added to it, but multiplied by it. Now, there's three possible cases here, because if we've got a function of x or a function of y that's actually equal to 1, then it could be sort of in disguise, or it could look like it's missing. So the most general case is where neither the function of x or the function of y are constants. So a case like that would be something like, for example, y dash equals, let's say, 2x. That's a very simple function of x. And the function of y might be something like y minus 1. This is just our basic sort of case. And these are the sort that we're going to be solving today. We're going to be separating them. If the function of y is equal to 1, then you'll end up just with y dash looking like some function of x. Now, I've written that these are really just indefinite integrals, and we've already learned how to solve these without separating them. So an example of one of these would be something like y dash is equal to, let's say, 2x. That's just a simple function of x. And we've already seen that we can solve that by saying y must be x squared plus some constant. That gives us a general solution, and we can find particular solutions if we've got a clue. Now, the last possibility is if the function of x is equal to 1. And in that case, it'll just look like y dash is equal to some function of y. The function of x will seem to be sort of missing. Now, we're going to look at these sort in the next lesson, so that's coming along later. For today, we're looking at the general case where we've got a function of x multiplied by a function of y. Okay, so how do we actually go about separating a differential equation that is of this special form that it needs to be if we're going to actually be able to separate it? Well, the first thing is, if you've got it written as y dash, change it to dy dx, and that will become apparent later because we need to actually do some cancelling of dx's at some point. So if it's of this form, let's rewrite it like this. Next, we need to divide both sides by the function of y, and that, in effect, is the separating part. We're taking the function of x and the function of y, which have to be multiplied by each other, and we're putting one of them on one side of the equation and leaving the other one on the other side. Now, we're going to bring the function of y across near the dy dx for a reason. So this is the one we need to divide by. So if it was in this form, then our function of y ends up on the bottom of a fraction with 1 on the top over here, and we've still got our dy dx, and we've still got a function of x. Then we need to integrate both sides with respect to x. So the only thing that's changed from this line to this line is that I've put the integral sign and I've put dx there, and I've just copied exactly what I had. Now at this point, our dx's can actually cancel there. Now they're not strictly a fraction, but they can behave like a fraction. The chain rule tells us that we can do that with our dx's, and we've done that before for various other processes. Now after that, what you get when you integrate both sides will depend on what your function of x was and what your function of y was. So you'll go ahead and just integrate both those sides independently. We only need to add a constant to one side or the other. And that sort of makes sense, because if you add a constant to both sides, it's not wrong, but you could easily tidy that up and say, well, if I take this one away from that one, really I only need to have one unknown. So add it to one side or the other. Then generally you'll need to tidy up your solution. It might be a bit messy or it might not, but rearrange it so that it's actually in terms of y. Because if we've started with y dash is equal to something and we're integrating that, we want to know what y is equal to. Now, all of that will give you a general solution. It won't give you a specific or a particular one though. To do that, you'll need to sub in some known value of x and y so that you can actually find the value of your constant. In this example, we need to solve this differential equation and then find the particular solution that passes through the origin. So first step is just to check that it actually is separable, and it is, because we've got a function of x multiplied by a function of y. So our first step is to rewrite y dash as dy dx. That's simple. And then the second step is to divide both sides by the function of y. Now I've actually got two choices here. I could choose to see this as negative 2x being the function of x and e to the y being the function of y. And that would lead me to say, let's divide both sides by e to the y. But I've actually got two choices, because I could let this negative sign belong with the function of x or with the function of y. which one am I going to pick? Well, at first it's not going to be easy to know. So just take your pick. It'll work out either way. It's just that the last step might be a little bit easier if you've made a certain choice. I'm going to this time divide by negative e to the y, and you'll see why as we go through. But I'll also do it the other way to show that you could still get the same result if you choose the other method. So first step, y dash becomes dy dx. Then we're going to divide by the function of y, and I've chosen to bring the negative along, which means that the other side is just 2x now. Now, here's a little tip. Leave a bit of space. In fact, let's leave a little bit more space in between your working here, so that then when you do the third step, you can do it straight on this line of working and not have to write everything out again. So just double check what we've done here. We've divided by the function of y, and so that the x's are still there, the y's are over here, and we've changed that to that. So that's all good. Next step is to integrate both sides with respect to x. Now that means we're going to put one of these symbols and the dx. Remember, the two of them together mean we're going to integrate whatever's in between those, and we'll put the integral sign and the dx over here too. Now at this point we can see that our dx's cancel. Now after a while you might be thinking, oh, I'm not going to bother writing that dx because I know there's going to be another dx there and it'll cancel. But I would discourage you from taking shortcuts in the beginning, because we really want to develop an understanding that when we take the integral of both sides with respect to x, it's actually performing an operation, and we need to perform the same operation to both sides of an equation to be sure that it's still balanced. So here you'll see that the whole reason now that we divided both sides by the function of y and not the function of x is that now we've got our y's over the left-hand side, and now that the dx's have cancelled, we're actually integrating with respect to y, which is great. We can pay respect to y because there's y's over here to pay respect to, and we can integrate with respect to x on the side that's actually got x's on it. So that's why we wanted to divide by the function of y in the first place, if that makes sense. Okay, so on the next step, we can actually integrate both sides. Now, if you need to take a line to tidy up, go ahead and do it. I can see that on this side, what this actually is negative e to the negative y. And if you want to rewrite it like that to make it simpler, go ahead. So now integrating this, I know I'm going to get e to the y, and then thinking about whether it needs anything out the front. If I differentiate this, the negative will come down the front, which it is, and I'll rewrite what I've got. So in fact, that is the integral of this side. And on the other side, integrating this, I get x squared. And you'll remember that I said you only need to add the constant to one side or the other. I tend to add it to the right-hand side, but it wouldn't hurt if we added it over here. Now, the reason I added it over there is that the next step is to tidy this whole thing up and get it in terms of y. So I'm trying to get everything on the x side as much as possible, and that's a great reason for putting that over here. So I've got e to the power of negative y is equal to x squared plus some constant c. And now I'm close to having it in terms of y. It's in terms of minus y at the moment. So I can multiply both sides by negative 1 and say I've got negative, and you can keep it log with base e, or you can write ln, and now we've got our x squared plus c. Now that's our general solution. We've been asked to find the specific solution that passes through the origin. So we would say when x equals 0 and y equals 0, we're going to have 0 is equal to the negative ln of c, because we've just got nothing plus c. Now, if I multiply both sides by negative 1 here, I can see that I can actually just get rid of that negative sign, because multiplying by negative 1, I can see it ends up like that. So now e to the power of 0 is equal to c, therefore c equals 1. So our specific solution that passes through the origin is y is equal to the negative log with a base of e of x squared plus 1, because we just found that our constant was 1. So that's our particular solution. Now, way back here, remember I said that there was another way that we could have done it. If we left our negative on the right-hand side with our 2x, then in the beginning we would have just brought our 1 over e to the y over here. We would have had our dy dx, and then our dx's would have cancelled the same way. But instead of having the negative over here, we would have had it on the other side over there with the 2x. Now, as we came to integrate this, we would say, all right, that's e to the minus y, which we now need to integrate with respect to y, and that's going to be equal to, integrating this, we'll get minus x squared plus c, and then integrating this part here, we can see that we're going to get negative e to the negative y, so that's a little bit trickier than what we had here. is going to equal negative x squared plus c. Now, this is not really a problem. It just means that we've got a whole lot more negatives involved, and bringing the negative over before actually made it disappear earlier. Now, don't get too hung up back here on trying to decide which is the easy way. Just get stuck in and go for it. But you'll get more of a feel for when you should bring the negative across and when you shouldn't, based on what these functions of x and y actually are. If you end up in this situation, don't worry, just multiply everything by -1, and what you're going to find is that these two terms tidy up nicely. You could call this minus c, and so then we're going to end up with a minus c in here. Now, is that a problem, adding c or minusing c? It's not, is it? Because if we're adding c and it's negative, or subtracting c and it's positive or negative, it actually makes no difference. So having this in here is another alternate solution that would be fine. But we tend to like adding a constant because that's something that's sort of in our vocabulary and it's, you know, a standard sort of thing to do. So what you could do here is you could actually change that and say we're adding some other constant called d, acknowledging that d is actually c times -1. Now, why would you give it a different letter? We are showing that they're not actually the same constant. They've got opposite signs. So following through from this working, you'd end up with the exact same thing from here, because this feeds straight across to just like that, except you might have a d in the place of a c, which is completely fine, and your particular solution would work out just the same way. Another example now, we need to solve a basic differential equation and then find a particular solution. So first step, let's change y dash to dy dx. Let's get our function of y on the other side. Now here, we've got our function of y is 1 over y. And if we're dividing by 1 over y, it's the same as just multiplying by y. The way to think of it is we need our function of y on the other side. So if I just multiply both sides by y here, it ends up over there. And on this side, I've got the x. Remember, I leave a little bit of room as well, so that then when I need my equal sign, then when I take the integral of both sides with respect to x, here my dx's cancel again. So I've actually just got y dy, the integral of y dy, and the integral of x dx. So this side integrates simply to y squared over 2, and this side is going to be x squared over 2, and we'll add our constant to one side or the other, generally picking this side. Okay, so now we've just got to tidy this up and get it in terms of y, or in this case, let's say y squared. If I just multiply everything by 2, these two terms are fine. I could write it as 2c, but remember c is just some constant anyway. So in a way it's neater to write this as d, acknowledging that if you have two c's, then you're going to get a d. Now, technically you could just write a c here again and say, look, we had c, we've still got a constant, but the fact that this constant is not the same as this constant makes me feel like we should use a different letter just to be really clear. Now, when we were looking at motion, we called subsequent constants C1, C2, things like that. But remember, they were quite different constants that weren't really related to each other. Whereas here we've taken some constant and done something to it. So I feel like we should perhaps give it a different letter. It wouldn't be wrong though to use C1 and C2. It probably isn't technically all that wrong to put a C in both places either. But I tend to just prefer if my constant has changed, I use a different letter. So now this is the general solution. We could say y is equal to the plus or minus square root of all of this. I'm not sure that that's necessarily a better form of this thing though. Now to find the solution that passes through 4, 5, let's just let x equal 4 and y equal 5. So therefore on this side we've got 25 is equal to 4 squared, that's 16, plus d. Now whether you call it c or d, you can see why it doesn't really matter too much here because we're going to find out what d is. In this case, d is 9. So then our particular solution is y squared is equal to x squared plus 9. Now this is a weird sort of graph. We haven't really graphed things like this before. It sort of looks almost parabolary up here and down here as well. It's got a sort of a weird sort of shape to it.